Black holes stand as the most terrifying, bizarre, and deeply unsettling objects that exist anywhere in our universe. They challenge everything we think we know about reality itself. So imagine for a moment that I decided to throw you into one of these cosmic monsters. And yes, I mean that quite literally. We are going to send you on a one-way journey into the heart of a black hole and observe firsthand how the fundamental laws of physics that govern our everyday experience begin to crumble and fail, giving way to phenomena so strange that they seem impossible even to imagine. Albert Einstein himself is reported to have described these extraordinary beasts as the place where God attempted to divide by zero when he first predicted their existence through his equations. The remarkable thing is that Einstein did not even truly believe that such objects could actually exist in our real universe. He thought they were merely mathematical curiosities, strange solutions to equations that nature would never actually allow. But we have found them. They are real. They are out there right now. So let us do exactly what I suggested. Let us send you on an incredible journey plunging deep into a black hole and watch together as the very fabric of reality warps and twists in ways that defy common sense, producing some of the most mind-blowing phenomena that physics can offer. Now, as you continue watching and reading along with this exploration, I need you to keep just one critical thing in your mind at all times. This is not science fiction. This is not some fantasy dreamed up by Hollywood screenwriters or science fiction authors. This is real physics, based on equations and observations that have been tested and confirmed countless times. And at various moments during this journey, what I describe might be genuinely hard to believe. Your intuition might rebel against what you are hearing, but I can prove every single thing I am about to tell you. The mathematics backs it up. The observations confirm it. So are you ready to begin this journey into one of the universe's most extreme environments? When massive stars, those with many times the mass of our sun, reach the end of their lives after burning through all their nuclear fuel, they undergo a catastrophic collapse. What they leave behind is nothing in the conventional sense. There is no surface that you could walk on if you somehow survived the journey there. There is no physical surface that you could reach out and touch with your hand. What the collapse of these massive stars creates is something known as a singularity, which is a single, profoundly mysterious point in spacetime that is said to possess infinite density and therefore produces infinite gravity. Think about that for a moment. Infinite density means all the mass of a star, perhaps 10 or 20 or even 100 times the mass of our sun, compressed down into a point with literally zero volume. It is a concept that pushes mathematics and physics to their absolute limits. Einstein's general theory of relativity, published in 1915, really provides us with one truly revolutionary idea that changed how we understand gravity forever. Gravity is not actually a force acting on objects the way Newton described it, pulling things together across empty space. Instead, gravity is simply spacetime itself bending and warping as a direct result of an object's mass and energy. Imagine spacetime as a flexible rubber sheet stretched out flat. When you place a heavy ball on that sheet, it creates a depression, a curve in the fabric. Other smaller objects placed nearby will naturally roll toward that depression. This is essentially how gravity works according to Einstein. Massive objects create curves in spacetime, and other objects follow the shortest paths through that curved spacetime, which we perceive as the force of gravity pulling them together. This framework completely explains how we are held in orbit around the sun, how the moon orbits Earth, and perhaps even more interestingly for our purposes today, why black holes are even black in the first place. Like I mentioned before, when you look at a black hole, or rather when you look at where a black hole is located in space, there is no physical black surface sitting out there like a dark planet or star. The singularity hidden at the very center is simply so incredibly dense, so impossibly massive for its size, that spacetime around it is warped and bent so dramatically that it creates what we can think of as a well with completely vertical walls. Actually, the walls are more than vertical. They curve inward beyond vertical, which is difficult to visualize in our three-dimensional thinking. This extreme warping makes it absolutely impossible for anything, even light itself traveling at the maximum speed allowed in our universe, to escape once it crosses a certain boundary. Because to escape from a region with this much gravitational pull would require you to accelerate to speeds faster than the speed of light, which we both know from the laws of physics is completely impossible. Nothing with mass can reach the speed of light, let alone exceed it. And even light itself, once it crosses that critical boundary we call the event horizon, cannot escape back outward. It is trapped, forever falling inward toward the singularity. When Einstein first looked at these mathematical results emerging from his own equations, he was genuinely not convinced that nature would actually allow something this absurd, this ridiculous, to exist in reality. The equations said black holes could exist, but Einstein believed there must be some mechanism, some natural law that would prevent such extreme objects from actually forming. In 1939, he even published a formal paper arguing that this entire idea of a star collapsing completely into a singularity was not convincing and probably did not actually occur in our real universe. He thought the mathematics was leading us astray somehow. Ironically, and this is one of the beautiful coincidences in the history of physics, that very same year in 1939, J. Robert Oppenheimer, yes, the Oppenheimer who would later become famous for leading the Manhattan Project, published his own paper alongside a fellow physicist named Hartland Snyder. Their paper took the opposite view and predicted that stars really could collapse under their own immense gravity into what we now call black holes. They showed mathematically how it could happen, step by step. History proved Oppenheimer and Snyder correct, not Einstein, at least on this particular question. One of the most fascinating aspects about black holes is that literally anything can become one. And I genuinely mean that in the most literal sense possible. Even you, yes you specifically, could theoretically become a black hole. Karl Schwarzschild, a brilliant German physicist serving on the Russian front during World War I, was the first person to discover an exact solution to Einstein's notoriously difficult field equations. He did this while serving in the military, which makes his achievement even more remarkable. The solution he found is actually quite simple and beautiful in its mathematical elegance, once you understand what it represents. The Schwarzschild solution essentially tells us that any object with mass, represented by the letter m in the equation, whether that object is a massive star, a planet like Earth, or even a small human being, can theoretically become a black hole if it gets compressed or squished down to fit inside what we now call the Schwarzschild radius, represented by the letter r in the equation. This radius depends only on the mass of the object. More massive objects have larger Schwarzschild radii, while less massive objects have incredibly tiny Schwarzschild radii. Let us take our Sun as a concrete example to make this more understandable. Our Sun has a mass of approximately 2 × 10⁻30 kilograms, which is an enormous amount of mass. Currently, that mass is spread out in a sphere with a radius of about 700,000 kilometers. But if you could somehow take all that mass and squeeze it down, compressing it into a much smaller sphere with a radius of just 3 kilometers, just 3,000 meters, you would create a black hole. The Sun would become a black hole if compressed to the size of a small town. That is how much empty space exists, even in seemingly dense objects like stars. What about Earth? Our planet is less massive than the Sun, so its Schwarzschild radius is correspondingly smaller. If you took all the mass of Earth and compressed it down into a sphere with a radius of around 9 millimeters, about the size of a small marble you might play with as a child, you would have an Earth-mass black hole. All the continents, oceans, atmosphere, everyone and everything on the planet, compressed into something you could hold between your thumb and forefinger. It sounds absurd, but the mathematics is clear. Now let us consider a human being. A typical human might have a mass of around 70 or 80 kilograms. To become a black hole, a human would have to be compressed down to something so unbelievably, incomprehensibly small that it is difficult even to express. We are talking about sizes much smaller than even a proton, which is already almost impossibly tiny. A proton has a radius of about 1 femtometer, which is 10 to the negative 15 meters. A human's Schwarzschild radius would be roughly 10 to the negative 25 meters, which is 10 billion times smaller than a proton. But if you could somehow be compressed to that size, you genuinely would become a black hole, a tiny quantum black hole that would probably evaporate almost instantly through Hawking radiation, but a black hole nonetheless. Now I think it is finally time that we send you on your journey into a black hole, but we need to decide which one we should pick for this thought experiment. We could pick a small stellar mass black hole, like the ones formed from collapsing stars. These might have masses of just a few times that of our Sun and correspondingly small event horizons of maybe 10 or 20 kilometers in radius. But that seems somewhat boring and also quite dangerous for reasons I will explain later. Let us go bigger and think about supermassive black holes instead. What about the true behemoths of the universe? These supermassive black holes lurk at the centers of most large galaxies, including our own Milky Way. These cosmic monsters have event horizons larger than our entire solar system. We are talking about black holes containing billions of times the mass of our Sun, with event horizons that could swallow the orbit of Pluto and keep going. These are almost incomprehensibly massive objects. But perhaps that is too much, too extreme for our thought experiment. Why don't we go for one a little closer to home instead? Let me introduce you to Sagittarius A star, often written as SGRA, which is the supermassive black hole sitting right at the heart of our very own Milky Way galaxy. You are actually orbiting this black hole right now as you read these words. because Earth orbits the Sun, and the Sun orbits the galactic center, completing one full orbit every 230 million years or so. Sagittarius, a star, has a mass of about 4 million times that of our Sun, and it is one of only 2 black holes that we have successfully taken an actual picture of using the Event Horizon Telescope, a planet-sized network of radio telescopes working together. The other black hole we have imaged is the much more massive one at the center of the galaxy Messier 87. So let us set up our thought experiment properly. Let us assume that you and I have somehow managed to fly out there in a spacecraft, traveling the roughly 26,000 light-years from Earth to the galactic center. We park our spaceship at a safe distance, let us say about 1 trillion meters away from the event horizon of Sagittarius A star. That is about 7 times the distance from Earth to the Sun, far enough that we should be reasonably safe from the black hole's influence. We are going to send you out from the spaceship toward the black hole in some kind of small pod or spacesuit. And while you free fall inward toward the event horizon, I will remain safely on board the spaceship and watch your journey through powerful telescopes. But here is the absolutely key fact that makes this journey so strange and counterintuitive. General relativity tells us that the way time is experienced by a person near a massive object like a black hole can be dramatically different from how time is experienced by someone far away from that mass. This happens because spacetime is so intensely warped and curved by the black hole's enormous mass. We saw this effect portrayed beautifully in the movie Interstellar, where the crew visits a planet near a black hole and experiences extreme time dilation. 1 hour on that planet equals 7 years back on the ship. So to keep careful track of time during your journey and understand exactly what is happening, we give you a special watch, a highly advanced chronometer that will simultaneously display 2 different times. One display will show you how much time has passed from your perspective, your reference frame as physicists call it, as you fall toward the black hole. The other display will show how much time has passed from my perspective back on the ship, watching you from a safe distance. We carefully synchronized this watch with the clock on the spaceship, making sure both read exactly the same time at the start, and then away you go on your journey toward the black hole. As your journey begins, you look ahead and see the distant monster that you are falling toward. It is rapidly consuming material from its surroundings, pulling in gas and dust from nearby space. This material forms what is called an accretion disk, a swirling disk of matter spiraling inward toward the event horizon. As the material in the accretion disk falls inward, it accelerates to tremendous speeds and begins to collide with other material also falling inward. These collisions cause the material to become superheated due to friction, much like how rubbing your hands together generates heat, but on a far more extreme scale. The accretion disk can reach temperatures of millions of degrees, hot enough that it glows brilliantly across the electromagnetic spectrum. I should mention that the simulation of a black hole accretion disk that scientists have created to understand what you would see is incredibly computationally intensive. Running such a simulation accurately would have taken more than a full decade, more than 10 years, to complete on a typical laptop computer. That gives you some sense of how complex the physics is that we are dealing with here. The disk in real life, if you could somehow see it with your naked eyes from this distance, would likely appear as a bright blue or even white color due to the extreme temperatures. But in many scientific visualizations, it has been rendered as orange or red for visibility reasons, to make it easier to see the structure and distinguish different parts of the disk. You check your special watch for the first time, curious to see what it shows. Only about 30 minutes have passed since you left the ship from your perspective. You have traveled quite a distance already, but you are still only about 0.1%, 1,000th of the way to the event horizon. The black hole is still very far away. When you look at the second display showing my time back on the ship, you see that I have experienced 30 minutes plus an additional 11 seconds. Not too bad so far. The time dilation is present but minimal at this distance. We are still far enough away that spacetime is not yet dramatically warped. You continue falling inward, and now we are getting noticeably closer to the black hole. The curved spacetime around the black hole is beginning to cause all kinds of strange visual effects that you notice around you. Light rays coming from stars and gas clouds that are to the sides of the black hole, or even behind it from your perspective, are being bent and curved around the black hole before arriving at your eye. This is the same gravitational lensing effect that astronomers use to study distant galaxies, but here you are experiencing it directly and dramatically. The black hole is acting like a giant lens in space, bending the paths of light rays that pass near it. Let us check your watch again. You have now been falling for 2 full hours from your perspective, 2 hours since you left the safety of the spaceship. You have covered much more distance and are now about 1.4% of the way to the event horizon. Still a long way to go, but making progress. But when you check the second display showing my time back on the ship, you notice something slightly concerning. I am now 44 seconds ahead of you. For me, 2 hours and 44 seconds have passed while you have experienced exactly 2 hours. The time dilation effect is growing stronger as you get closer, but it is still not too dramatic. Slightly alarming perhaps, but nothing crazy yet. As you continue falling and getting closer, you notice that the shadow of the black hole, the dark region in the middle of your field of view where no light can escape, appears to be growing faster than you would normally expect based on your rate of approach. This is happening again due to that gravitational lensing effect we mentioned earlier. Light rays that would normally pass by you and continue on into space are being bent by the curved spacetime around the black hole, redirected into your retina. This makes the black hole appear larger than its actual geometric size would suggest. The black hole is bending light from behind and around itself into your view, making it seem to take up more and more of your visual field. After quite a long time falling inward, you finally check your watch again, and what you find genuinely terrifies you. From your perspective, your reference frame, you departed from the ship around 12 hours ago. Half a day has passed for you. You are tired, probably hungry and thirsty, and the journey is taking longer than you might have hoped. But when you look at the second display showing my perspective back on board the ship, you see that I have been watching you float toward the black hole for nearly 15.5 hours. We are now talking about a difference of several hours. The time dilation is becoming severe. We are getting quite close now to the event horizon, and things are genuinely about to get extremely weird, stranger than anything you have experienced so far. But before you reach that point of no return, that boundary beyond which even light cannot escape, you come across a strange and seemingly magical place in space. If you could somehow be frozen in time at this one special spot and looked carefully around at your surroundings, you would not believe what your eyes showed you. You would think you were hallucinating or dreaming. You have arrived at what physicists call the photon sphere, which might genuinely be the strangest, most counterintuitive place in our entire known universe. The photon sphere is a region of space around the black hole, located at precisely 1.5 times the Schwarzschild radius, where gravity is perfectly balanced in just the right way such that light, photons of electromagnetic radiation, can actually enter into stable orbits around the black hole. Not matter that is emitting or reflecting light, but the photons of light themselves, massless particles traveling at light speed, can be trapped in orbit around the black hole. Let me be more precise about what is happening here. If light moving through space arrives at the photon sphere moving tangentially, which means perpendicular to the radial direction toward the black hole, it can enter into a circular orbit and continue circling the black hole indefinitely. But this orbit is incredibly unstable. Any tiny variations in the photon's path, any slight deviation inward or outward, will cause the careful balance to break. If the photon's path curves even slightly inward, it will spiral down into the black hole, falling past the event horizon and eventually reaching the singularity. If the path curves even slightly outward, the photon will escape to infinity, flying off into space. Under these very specific and precise conditions of being at the photon sphere, if you just remained frozen at that location and carefully looked around in all directions, you would see multiple mirror images of yourself looking away from you in various directions. You would see several copies, perhaps an infinite number depending on how carefully you look, of the back of your head staring off into space. Light reflecting off the back of your head could travel around the black hole, completing a full orbit or even multiple orbits before arriving back at your eyes. You would be literally seeing yourself, essentially standing right beside you in real time with no mirrors, no technology, no tricks, just the natural warping of spacetime itself creating these impossible views. It is one of the most bizarre predictions of general relativity. And here is where things truly begin to get crazy and difficult to believe. As you continue your journey inward past the photon sphere, you are getting really quite close to the event horizon now, that boundary of no return. We are now past the photon sphere, deeper into the black hole's gravitational well. The black hole seems to be taking up far more of your entire field of view than you would expect based on simple geometry and your distance from it. It feels like you are being swallowed by darkness, like the darkness itself is alive and consuming you. This is happening because the darkness, the shadow of the black hole, is being gravitationally lensed and warped around you in space. You are seeing not just the part of the black hole's shadow that would normally be visible to you if spacetime were flat, but also the back and sides of the black hole's shadow, curved around into your view by the intense gravitational field. The black hole is showing you parts of itself that should be hidden behind it from your perspective. Let us check your watch again. You have now been falling for 13 hours from your own perspective. You are exhausted, perhaps terrified, and the watch tells you something shocking. In just 24 more minutes, you will cross the event horizon. 24 minutes separate you from the point of no return. But when you look at the second display showing my perspective back on the ship, you see that I have been watching your journey for nearly 20 whole hours now. 7 hours longer than you have experienced. The time dilation is becoming extreme. 18 minutes pass from your perspective. Just 18 minutes, the time it might take to watch a television show or cook dinner. You check the watch again, and now the difference is staggering. I have been watching you for nearly 40 hours back on the ship. Almost 2 full days have passed for me. The last 18 minutes that you just experienced, that felt like a normal 18 minutes to you, lasted 18 hours for me watching from a distance. Time is stretching and distorting dramatically. And finally, the moment arrives. After just 6 more minutes by your watch, you cross the event horizon of the black hole. This is it, the point beyond which nothing, not even light itself, can ever escape back to the outside universe. You close your eyes for a moment, take a deep breath to calm yourself, and then look down at your watch to see what it says. But something seems to be broken or malfunctioning. The display showing my time back on the ship appears to have frozen, or perhaps is displaying an error. It seems to be saying that I have been watching you fall inward for an infinite amount of time. Infinity. The watch must be broken, you think. But it is not broken at all. The watch is functioning perfectly. The physics it is displaying is exactly right, as strange and impossible as it seems. I have spent decades, perhaps centuries or millennia, watching you slowly edge closer and closer and closer to the event horizon, never quite reaching it from my perspective. Eventually, I see you become redshifted, which means the light reflecting from your body becomes stretched to longer and longer wavelengths by the intense gravitational field. You begin to glow red, then infrared, invisible to human eyes. I have to use an infrared telescope to even see you anymore. Then you fade into radio wavelengths and beyond. From my perspective safely back on the ship, I never actually get to see you cross the event horizon, even if I lived forever, even if I watched for billions or trillions of years. The last 6 minutes of your journey, those final 6 minutes before you cross the event horizon, literally last an eternity from my reference frame back on board our ship. Time dilation becomes infinite at the event horizon. I know this sounds like complete science fiction, like an absolute fantasy invented by a creative writer, but it is not fiction at all. This prediction jumps directly out of Einstein's equations with no ambiguity. The mathematics is clear. Now you are inside the event horizon, past the point of no return. So what happens here in this region that no information has ever escaped from to tell us about? Strangely, you would actually have a pretty hard time knowing exactly when you cross the event horizon itself. There is no sign, no boundary marker, no sensation of passing through something. You can still look outward into the universe, seeing distant stars twinkling, galaxies shining, and you can even still see our spaceship floating out there in space where I remain watching. But all of that light that is reaching your eyes, just like you yourself, is now entirely destined to fall toward the singularity. That light from distant stars is also trapped inside the event horizon now, falling inward alongside you. You are completely and irrevocably past the point of no return. Ahead of you, hidden somewhere in the darkness, lies the singularity. That point of infinite density where our known laws of physics completely collapse and break down, where time itself simply stops or perhaps loses all meaning. To escape the inexorable pull of the singularity now that you are inside the event horizon, you would need to accelerate and travel faster than the speed of light, which we know with absolute certainty is impossible. Nothing can travel faster than light. Not spaceships with impossibly advanced technology, not even light itself can exceed its own speed. The singularity will claim you inevitably. A common misconception that appears in some popular science discussions is that if you were inside the event horizon and looked out into the universe, the intense time dilation effect would cause you to watch the entire future history of the universe unfold dramatically in front of your eyes like a fast-forwarded movie. You would see stars born and die, galaxies collide and merge, perhaps even witness the heat death of the universe itself, all in the span of moments from your perspective. But this is just not true according to the actual physics. This is not what would happen. Due to a relativistic effect called aberration, which describes how the apparent direction of light changes when you are moving at high speeds. As you approach closer and closer to the singularity at the center, you would watch the outside universe appear to get compressed and squished into an increasingly thin little ring of light around you. The view of the external universe would not expand and fill your vision. Instead, it would contract into a smaller and smaller circle, eventually becoming just a narrow ring, and then perhaps fading from view entirely as you approach the singularity. And finally, once you are genuinely close enough to the singularity itself, the tidal forces become impossible to survive. Tidal forces are differences in gravitational pull across an extended object. Your feet, being slightly closer to the singularity than your head, would experience a stronger gravitational pull. This difference would stretch you out, elongating your body. Your feet would be pulled away from your legs stretched out in front of you, dislocating joints and tearing tissue in a process that physicists have nicknamed spaghettification. You would be stretched like spaghetti, thinner and thinner, until the molecular and then atomic structure of your body itself is torn apart. You and the black hole become one, your matter joining the singularity. You and the black hole will wander the universe together for eternity, or at least until the black hole itself eventually evaporates through Hawking radiation billions upon billions of years in the future.